let's discuss how to find a volume over the general regions using the double integration. So we are given some surface and we would like to choose some region on the xy plane, and we would like to just cut over our surface over this region, right? Basically, I would like to cut the surface from here, here, here only, and I would like to find the volume of this piece. And in order to do this, let us look to this surface on the xy plane. So our surface might be given in this form, where the x is going to change between the constants a and b, and the y is going to change between the two functions, right? So for example, if I choose some x here, x0, for this x, y is changing between these 2 points. But if I choose another x here, x1, the y points are going to change between these 2 points, right? But in general, depending on which x we choose, the y points, y coordinates of the points are going to change between this function and this function. Or this region D might be given using this form. Again, with the same idea, when we choose some x0, the points along this line, or actually the y coordinates, are going to change between this function and this function. So we can define all the points in this kind of regions using this notation. So the D is going to be some region in the form of the points, right, which are given with the two tuples, where the x is going to change between the two constants, and whenever you fix one of the values for the x, the y is going to change between the values of these two functions at this fixed value of the x. So what we want is, we would like to find how to integrate the double integration over this kind of regions. So when the x changes between the two constants and the y coordinates of the points inside this region are changing between the two functions, we call this type of the region as type 1 region. And we would like to evaluate this double integration by integrating our function f of xy with respect to the y first, where the boundaries would be g of x1 and g of x2. Please note that when we integrate this function with respect to the y, we fix the x, so we consider the x as a constant. So you need to integrate this function with respect to the y. Then once you integrate it, you need to evaluate this definite integral with these boundaries, with these functions. So at the end, you need to get some function which depends only on the x. Then we have to integrate this with respect to the x from a to the b. So it is really important that when the y changes between the two functions, you should integrate this function with respect to the y first, then with respect to the x. So let's do an example. What we would like to do is, we would like to integrate this double integration over the region D, which is located between these two parabolas. So in order to understand what does it mean, so in order to imagine this, so let's try to draw these two parabolas. So the parabola y is equal to the 1 plus x squared is easy to draw. Y is equal to the 1 plus x squared is very similar to the y is equal to the x squared. So we know how to draw the y is equal to the x squared, and y is equal to the x squared plus 1. It means that this is like 1 unit upper than y is equal to the x squared. And y is equal to the 2x squared is also similar to the y is equal to the x squared. But if you remember, if you multiply a function, the x to the t, it means that it is going to be shrinked. It is going to be more narrower. So this is going to be similar to the y is equal to the x squared, but shrinked. And our region D is defined here between these two parabolas. So I can find this intersection points by solving the system of equations. If I equalize the y is equal to the 1 plus x squared, y is equal to the 2x squared. If I solve the system, it is going to give me the coordinates of the 2 points which are on the intersection of the two curves. So I would solve this by equalizing them. It would be 1 plus x squared is equal to the 2x squared. From here I can find the x squared is equal to the 1. From here I can find that the x is plus minus 1, right? So the coordinates of this point, x coordinate of this point is minus 1. The coordinate, x coordinate of this point is 1. So I can define this region in the notation of the set as, so the set D is all the points in the form of x and y, where x is going to change between minus 1 and 1. And whenever I choose the x, for example, if I choose some fixed x here, 0.5 5 with the minus, the y points of the points inside this region are going to change from this until this point. And if I choose, for example, x to be equal to the 0, y coordinates of the points inside this region are going to change between these 2 points. So depending on which x I chose, the y coordinates of the points inside the region are going to change between the 2 functions, basically between the 2x squared and 1 plus x squared. So you fix some value for the x, then you have to substitute it to here, and it tells you how the y coordinates of the points inside the set are changing. If I would like to integrate this function, so x plus ty is a double integration over this region D, then I would first of all integrate this function x plus ty with respect to the y, because y is changing between the 2 functions, between tx squared and 1 plus x squared. Then I would integrate this with respect to the x between minus 1 and 1. Let's integrate this first of all with respect to the y, and let us write it separately. When I integrate this with respect to the y, please note that the x is fixed. We look to the x as a constant. So x is a constant, y is a variable, so that is why the antiderivative of this function would be x multiplied as a y, right? Because x is a constant, plus y squared. So we need to put here 1 plus x squared and tx squared. So if I substitute everything here, it would be x multiplied as a 1 plus x squared plus 1 plus x squared in the square minus x multiplied as a tx squared minus tx squared in the square. So if I open up all the brackets, I would get x plus x cubed plus 1 plus tx squared plus x squared minus x tx cubed minus 4x in the power of 4. And I can write this in the form. So 1 plus x plus tx squared, because I have only tx squared, minus x cubed minus 3x in the power of 4. So this is all which I have. And I need to integrate this function, 1 plus x plus tx squared minus x cubed minus 3x in the power of 4 with respect to the x, where x changes between minus 1 and 1. So integrating this polynomial is very straightforward, and we can write down the antiderivative in this form, x plus x squared over t plus x cubed over 3 minus x4 over 4 minus x5 multiplied to the 3 over 5. So if I put the values between 1 and minus 1, so these two terms are going to be cancelled because they have the even powers. And what I will have here is the values for these terms multiplied to the 2. So I can write this multiplied to the 2, 1 plus 1 over 3 minus 3 over 5. So if I give the common denominator, it would be 2 multiplied to 15 plus 5 minus 3 over 15. And this would be 34 over 15. So when the region is given in this form, where the x points are going to change between the 2 functions and the y points are changing between the 2 constants, 2 lines, between d and c and d, this type of the region is going to be called type 2 regions. And we are going to define this region in this way. So we would fix the y to here, for example, some point y1. Once you fix this, the x coordinates of the points inside this region along this y1 line will change between these 2 points. Or if you fix the y to be equal to here, and again the x coordinates of the points inside this region along this line would change between these 2 points. So you see, so depending on which y you're choosing, the points x coordinates are changing between the 2 different points which are defined between these 2 functions. What does it mean? It means that I can change the y coordinates inside this region between c and d, and the x coordinates would change depending on which y I've chosen. It would be between the 2 functions h1 of y and ht of y. And this kind of region is called type 2 region, where the x is going to change between the 2 functions and y is going to change between the 2 constants. And if I would like to evaluate the double integration of some surface over this region, and I would integrate this surface first of all with respect to the x, because x changes between the two functions, and I would put the borders, the functions, h1 of y, ht of y. Then once I integrated this, I would get some function which depends only on y. And then I would integrate this with respect to the y from c to the d. And the final result would be a constant. So in order to understand how it works, let's do an example. We are given some surface, z is equal to the x squared plus y squared. We would like to find a volume under the surface over the region which is bounded by these two functions. Y is equal to the tx and y is equal to the x squared. So I can draw these functions like this. So y is equal to the x squared is simple parabola, which is drawn like this, and y is equal to the tx is also a simple line, and the region, our region D, is defined here. And actually we can define this region using the both types. So if I would know the coordinates, so I can find the coordinates of the points here and here. In order to do this, we need to solve the system. Y is equal to the x squared, y is equal to the tx. We need to solve the system. So this system has a solution: x squared minus tx, or is equal to the tx. X squared minus tx is equal to the 0. So one of the values for the x is equal to the 0. The another one is 2. So if you substitute this to one of these equations, you would get y1 is equal to the 0, yt is equal to the 4. What does it mean? It means that the coordinates of this point, intersection point, is 0 and 0. This is the point 1. And the coordinates of the second point is 2 and 4. So do you remember we defined the type 1 as the region where x is going to change between the two constants, right? So in our case, it is going to change between 0 and 2, and y would change between the two functions, right? So which is lower? The lower function is x squared, and the upper function is tx, between x squared and tx. So if you integrate our surface over this region, you would just choose the borders of the integration like this. Now we can try to define this border using the type 2, where the y would change between the two constants, right? It would be 0 and 4. So d of the type 2 would be the points x and y, so that the y would change between 0 and 4, and x would change between more lefter function in terms of the x, more lefter function in terms of the x would be x is equal to the y over 2, until more righter function. More righter function here is x is equal to the square root of y with the plus sign. Square root of y. So we would integrate our function like this as well, so in order to get the answer. So now let's try to do one of them. We can try to do the type 2. So we need to integrate x squared plus y squared as a double integration over the d. So let's call this as over dt with respect to the dx dy. So first of all, we need to integrate this function with respect to the x, where the borders are going to be y over t and square root of y, and the y would change between 0 and 4. So let's integrate this. So when I integrate this function with respect to the x, I need to look to the y as a constant. It would be x cubed over 3 plus y squared multiplied to the x. We need to put the values of y over t and square root of y. So let's substitute the square root of y to here instead of x, right? Because once we finish, this function should depend only on y. It would be y 3 over t divided to the 3 minus y squared plus y squared multiplied to the square root of y minus y cubed over 24 minus y cubed over 2. So now we need to integrate this with respect to the y. If I give the common denominator, it would be 12 here, right? And I would get y 3 over t over 3 plus y, so 2 plus half, it would be 5 over 2 in the power, minus y cubed minus 12 y cubed, it would be minus 13 y cubed over 24. So we need to integrate this with respect to the y, where the y would change between 0 and 4. So let's integrate this. When we integrate this, we're going to use a simple rule for the power functions. Y in the power of 5 over 2. so 3 over t plus 1, divided to the 3 multiplied to the reciprocal of the 5 over t, t over 5, plus y in the power of 7 over t, multiplied to the reciprocal of the 7 over t, which is t over 7, minus 13 over 24 multiplied to the y in the power of 4 divided to the 4, and we need to substitute the 0 in 4. If we would substitute the numbers, the 4, and if we would evaluate this, we would get 216 over 35.